Third section of chapter 10. This is a section that I alluded to a few chapters ago when we were working with vectors in 2 dimensions. We learned about the dot product, and I told you that that was one of the 2 different ways of multiplying 2 vectors together, but there is another way that we will see later. Later has come. So today we're going to be looking at what's called the cross product of 2 vectors. We're going to see what it is, we're going to see some properties of it, and we're going to see an application of it. So the cross product, first deal, how to find it. So we start out with 2 vectors. These are the 2 vectors that we use. Like when we have a vector, it's going to be like vector u is going to be u1, u2, u3. Vector v is v1, v2, v3. Towards the end of the lesson, we'll actually have a vector w, which is w1, w2, w3. This is just written out in unit vector form, where we have the I, j, and k vectors that we saw a bit in the past couple sections. So, to find the cross product between these 2 vectors, you just take u2 times v3 minus v2 u2 times v3 minus u3 times v2, then that becomes your x coordinate, your I coefficient, and then etc., etc. It's not a hugely complicated formula as far as doing it. I mean, it's a couple multiplications and subtraction, but it's really long and not particularly user-friendly. What's nice about this is if we look at what we're doing, this u2 v3 minus v3 u3 v2 looks a lot like something that we've seen before. That looks a lot like the determinant. In fact, another way of finding the cross product, instead of using that formula, this is the exact same thing as the determinant, where we put I, j, and k at the top, and then we have our first vector, and then our second vector. And the order is important. We're going to see on another slide or two, u cross v is not the same as v cross u. It's close, but not exact. So it's important that this first one becomes that middle line, and the second one becomes the bottom line. And then we just find the determinant. Well, how do we find the determinant of these? Well, we're going to do a problem or two here, but remember we're going to take these 2 and we're going to repeat them, and then we're going to multiply and add and multiply and subtract. So let's see an example of this, shall we? So we have our 2 vectors. U is I plus 3j plus 2k, and v is negative I plus 4k. So we're going to do our cross product. So we'll have u cross v, which is going to be the determinant. We'll have I, j, and k at the top, and then u, this is 1u, so we'll have 1, 3, 2, and then v is negative 1. We have 0 j's. Make sure that you include that in the right place. We wouldn't want to put negative 1, 4, then 0, because that positioning is important here. So negative 1, 0, and then 4. And now we're going to repeat these first 2 columns. So we'll have an I1, negative 1, a J3, and a 0. And now we're going to take our diagonals and we're going to multiply each of those together. So we're going to have 3 times 4 times I, which 3 times 4 is 12. So we'll have 12I plus negative 1 times 2 times j, so that's negative 2j, plus 0 times 1 times k is 0k. We wouldn't have to put anything, but I'm going to put plus 0k just so that we know it's there. And then minus, we're going to do these diagonals. So we have negative 1 times 3 times k is negative 3k plus 0 times 2 times I is 0I plus 4 times 1 times j is 4j. There's really nothing we can do to simplify these inside the parentheses, but we do have some common terms, some like terms. So let's distribute this negative here. Make that a plus, that's a minus, and that's a minus. And now we can combine our like terms. So we have i's, we have 12i minus 0i is going to be 12i. And then j's, we have negative 2j minus 4j is minus 6j. And 0k plus 3k is plus 3k. So u cross v is 12i minus 6j plus 3k, which you could also put in component form if you wanted to. 12, negative 6, 3. But this naturally comes out into that unit vector form. So unless it's specifically requesting component form, or you just really like component form, prefer that, you can leave your answer in the unit vector form as well. But going back and forth between them should not be too difficult at this point in time. So that's how to find it. It goes back to that determinant that we learned how to find way back in our matrix chapter. And I know that it's like, oh, wait, but there's that determinant feature on the calculator. Why can't we just use that? Well, that works until you have a variable thrown in there. And remember I'd throw like that one x in there? Well, we have I, j, and k. You can't use your calculator to find the determinant on this. You have to do it by hand. So that's one of the reasons why we learn how to do it by hand. Thankfully, we've got this nice method instead of the crazy one with all the other stuff that I had to do when I learned it. So that's how to find a cross product. Think you have it? Well, let's try one. So we have the vector u is 2, negative 3, 1. Vector v is 1, negative 2, 1. I put it in component form in this case. But go ahead, find the cross product, try your hand at it, pause the video. Once you're done, you can unpause it, and then we'll see how you did. So how was that? So let's try this out. We have u cross v is going to be the determinant of I, j, k. Then we have 2, negative 3, 1, 1, negative 2, 1. Then we'll expand it. I2, 1, j, negative 3, negative 2. We'll do those first diagonals, which will be negative 3 times 1 is negative 3i. 1 times 1 is 1j. That was a plus. Negative 2 times 2 is negative 4k. Minus. Let's go this way now. We have 1 times negative 3 is negative 3k. Negative 2 times 1 is minus 2i. And 1 times 2 is 2j. We can distribute this negative and then combine our like terms. I's, we have negative 3 of them plus 2 of them is going to be negative I. We have the j's. There's 1j minus 2j's is minus j. And we have k's, negative 4k plus 3k is minus k. So our cross product, u cross v, is negative I, negative j, negative k. Is that what you got? Hopefully it was. If not, did you see where you may have made a mistake? There's a few moving parts in this. Another thing that this will have you do is it'll tell you to show that it's orthogonal to both the two vectors. Now we're going to get to that in just a second on what it is. But a cross product is orthogonal to both the vectors that make it up. So u cross v is orthogonal to both u and v. Now, what does orthogonal mean? If you remember from the last time we looked at vectors, orthogonal is really a fancy three-dimensional word for perpendicular. U and v make a plane. Any two vectors make a plane as long as they are not the same, like as long as they're not parallel. Any two vectors that intersect make a plane. Yes. And so this orthogonal vector is it's perpendicular to that plane. So it's perpendicular to both u and v. U and v may or may not be perpendicular to each other. That doesn't matter. But the cross product is perpendicular to both. How can we tell if something's perpendicular? If we remember way back when, the dot product, if the dot product is 0, it's perpendicular. If we remember our dot product, or our angle equation, the cosine of an angle in between them will equal u dot v divided by magnitude of u times magnitude of v. If this equals 0, that means that cosine of 90 is 0, so that means they're perpendicular. So as long as the dot product equals 0, they are perpendicular. So we could test that. We'll check it with just one of them here. We'll check it with u. So we have the 2, -3, 1, and the 1, -1, -1, -1. They are all negative. Look at that. So the dot product, remember we just multiply. So we'd have the x components multiplied together. So we have, my 2 didn't show up, 2 times -1, then plus the y components, -3 times -1, plus the z components, 1 times -1. Something is not working out here. -1, -1. Oh, actually, no, it is. Never mind. I missed that we had 2 negatives in that middle. I thought we had 3 negative numbers here. So we have -2 plus 3 plus -1, which is 0. And that same thing will happen if you do the dot product with v and the cross product. You're going to end up with 0. So when it tells you to show that they're orthogonal to both vectors, that's all you do. You just find the dot product. So, into some properties of the cross product. The first one, if you switch the order, so I mentioned that the order is important. If you switch the order, it becomes negative. If you think about it, all the equations are like u2 v3 minus u3 v2. If we switch the u's and the v's around, we're just switching these two, and so instead of like a minus b, we end up with b minus a. So it just becomes negative. And so that's what happens with all of those properties. So if you switch the order of the cross product, you just make everything negative. It's distributive through addition. So u cross, if we have v plus w, we can do the cross product of each of them separately. And then add those two together, which is convenient if we have a variable in there. If we have a constant times the cross product, we could multiply that constant to either of the two vectors, not both of them. We could multiply it to either of them and then do the cross product. If we do the cross product with the 0 vector, remember the 0 vector is just 0, 0, 0, or 0i plus 0j plus 0k. We get the 0 vector because, again, back up to our equation, if these have 0 in them, we're going to have 0 minus 0, which will be 0 times I, plus 0 times k, plus 0 times j. So crossing it with the 0 vector does give us 0, and it doesn't matter which order we do that in. If we cross it with our itself, it's going to be 0, because if we do that, we'd have like u2 times u3 minus u3 times u2. That's going to be 0. And if we do a dot product with the cross product, this u dot v cross w, we can actually switch the order of that. That could be u cross v dot w. Notice the order there is important because we can't switch the v and the w. If we did, we'd end up with a negative, which wouldn't be the worst thing in the world. But the order there is important. And you might be thinking like, well, this is kind of a silly thing. Why would we ever do this? This is called the triple scalar product. And that's actually something that we're going to see in a couple slides. It's something that is actually relatively useful and not as difficult to find as you might think. We have some geometric properties of the cross product too, because we've been talking about this for a while, and you're probably thinking like, all right, but I mean, what does this even do? It's like, okay, it's orthogonal. Yeah, it is orthogonal, which we had mentioned. And again, u and v might not be perpendicular to each other. They might not be orthogonal to each other. That's okay. They still make a plane, and then the cross product is going to come out of that vertex of those two vectors and just go directly out. So like on your piece of paper, it would come directly up, out at you. The magnitude of u cross v, so the magnitude of the cross product equals the magnitude of u times the magnitude of v times sine of theta, which we could do a little bit of division to get sine theta equals the magnitude of u cross v over magnitude u magnitude v, and that gives us another way of finding that angle in between u and v, because that's what that angle is. It's not the angle in between the cross product, that's the angle in between u and v itself. That again is another one kind of like the one that we saw a couple slides ago, where the cosine of theta is u dot v over the magnitude of u times the magnitude of v. Which brings me to something I forgot to mention. So the dot product gives us a scalar. It's just a number. The cross product gives us a vector as our answer. U cross v equals 0 if and only if u and v are scalar multiples of each other, which is parallel, which is basically the same vector, but with that extra multiplier added in. And that can go back to that equation with the u2 v3 minus u3 v2. If one of them has a number multiplied to it, say 7, you could factor that 7 out of both those two products, and you'd end up with 7 times 0, which is going to be 0. And that would happen for each of the three components. So a way to tell if they're parallel is to take the cross product to see if it turns out to be 0. And then the magnitude of u cross v is the area of the parallelogram with u and v as adjacent sides. So that means we have parallelogram. This would be u, this would be v, and going from that base. So we can find the area of a parallelogram here with a cross product. Fun story, if you cut it, you have a triangle. So if you do 1/2 of the magnitude of the cross product, you get an area of a triangle, which is something else you're doing. How many ways do we have to find the areas of triangles now? It's crazy. I love it. But let's try finding the area of a parallelogram with these are its sides. And this is problem 38 too, by the way. So we're going to find the magnitude of the cross product. So first we have to find the cross product. U cross V is going to be the determinant. We're going to have IJK, and then -2, 3, 2, 1, 2, 4. Repeat the first couple columns, I -2, 1, J, 3, 2. We're going to find the cross product. So U cross V will be, let's do the first one. We have 3 times 4, which is 12I, plus 2 times 1, which is 2J, plus -2 times 2 is minus 4K, minus, go the other way, 1 times 3 is 3K, plus 2 times 2 is 4I, plus 4 times -2 is -8J. We can combine our like terms. U cross V, we have I's, we have 12I plus 4I is 16I. J's, 2J minus 8J is minus 6J. Except that I forgot to distribute that negative sign. This is a public service announcement. Make sure you distribute your negative signs. Otherwise, you will feel the fool. It's never good. All right, let's try this addition again. 12I minus 4I is 8I. 2J plus 8J is 10J. And -4K minus 3K is minus 7K. Now we need to find the magnitude of U cross V. So the magnitude here, we're going to take the square root, and then we're going to square all these and add them together, just like we did last time. So we'll have 8 squared plus 10 squared plus 7 squared. Remember that negative sign doesn't matter. We're squaring it, so it's going to be positive. So U cross V is going to be the square root of 8 squared is 64, plus 10 squared is 100, plus 7 squared is 49, which will give us U cross V be the square root of 213. I believe I'm going with 213 as my final answer on this one, which is not going to have a pleasant square root. You can get a decimal approximation for it or leave it as the square root of 213. But that's going to be the area of the parallelogram that has these two vectors as adjacent sides. Notice they're not the opposite sides, the parallel sides. They're just two non-parallel sides. So those are some geometric properties of the cross product, which brings us to that triple scalar product that we talked about. So first we want to know how to find it. So U dot V cross W. We could do V cross W and then do the dot product with U. It's not horrible to do that. However, it also has this fun equation where it's finding a determinant, but instead of that ijk in that top row, we have the u vector. This one, they are all numbers, so yes, you could actually use your calculator to find this. We're not going to because my calculator is sitting actually next to me within arm's reach, but it's turned off and I'm really too lazy to turn it on, so we're just going to do it by hand. So this is how to find it. So let's find one. This is question 49. We have u, v, and w. So we're going to find the triple scalar, u dot v cross w. It's going to be the determinant of u was 2, 3, 1. V is 1, negative 1, and then we don't have a k, so that'll be 0. And W is 4, 3, 1. We're going to repeat those first two columns. And now we can find our deal. So we have 2 times negative 1 times 1 is going to be negative 2, plus 3 times 0 times 4 is 0, plus 1 times 3 is 3, minus, go the other way, 4 times negative 1 times 1 is negative 4. 3 times 0 times 2 is going to be plus 0. Plus 1 times 3 is 3. Now we're not going to forget to distribute this negative sign because who would do a silly thing like that? So we can distribute that. And then actually we don't need to combine like terms. We can actually just do that. We didn't need to distribute the negative sign here. Negative 2 plus 0 plus 3 is 1. Well, it's plus. I already distributed it. May as well keep it there. Usually I would do 1 and then I would do the other, then I'd just subtract the two numbers, but I'm still traumatized from my previous mistake. 4 minus 0 minus 3 is 1. 1 plus 1 is 2. So u dot v cross w equals 2, which should not surprise you that it comes out to be a number, because remember, the cross product here gives us a vector, but then when we take the dot product of two vectors, we get a number. So that's where it comes out to be a number. So that's what the triple scalar product is, or it's how to find it. The question though is, what is it? Like, why would we find that? What are the geometric properties of this? Well, the volume V of a parallel pipette with vectors u, v, and w as adjacent edges is the absolute value of the triple scalar product. It's absolute value because the volume is going to be positive, and depending on the order you put your vectors into your matrix, you might get a positive or you might get a negative. It's that whole u cross v is negative v cross u thing. And so we just take the absolute value because that'll give us that positive answer. So now you may be thinking to yourself, self? I have to say that, make sure I'm paying attention. Self? What exactly is a parallel pipehead? Well, I'm glad you asked that question. A parallel pipehead is something kind of like this. It's like a rectangular prism, like a box, but you sat on the box and so it's all tilted. The sides are parallelograms, where like the front and back will be the same. The top and bottom will be the same. The left and right will be the same. So again, it's kind of like a box, except it's tilted. And you guys are lucky because I cannot draw this on my board to save my life, but I can insert a photo of it. So there we go. So what if we wanted to find the volume of a parallel pipehead with these as adjacent edges? And adjacent edges would be 3 edges that all hit one vertex. So this could be like U, V, and then W back there. Like, so those are 3 adjacent edges. They all share one common vertex. So find the volume of this, which is just finding the triple scalar product and then making sure it's positive, so taking the absolute value. It's what we just did. Take this chance to practice, pause the video, work out the problem, then when you're ready, go ahead and push play. Did you get it? Did you remember to to take the absolute value so your volume's positive? I hope so. Let's try this out. So the volume, oh, I'm still on red. The volume is going to be the triple scalar. So U is 1, 1, 3. V, we have 0 i's, and then 3, 3. And then W, we have 3, we have 0 j's, and 3. Having zeros in your finding determinants makes it so much nicer. Then we'll repeat the first two columns, 1, 0, 3, 1, 3, 0. We're going to do our first multiplications. 1, 3, 3 is 9, plus 1, 3, 3 is another 9, plus 3 times 0 is 0, minus 3 times 3 times 3 is 27, 0 times 3 times 1 is 0, and 3 times 0 times 1 is also 0. So 9 plus 9 is 18, minus 27 plus 0 is 27. 18 minus 27 is negative 9, but we need the absolute value of that. So our volume equals 9 cubic units, whatever units they were talking about in this case. This one was just a naked problem, so we didn't have units. But that's still how to find it. Did you get 9? If not, did you see where you went wrong? So this is the cross product. Lots of determinants of a 3 by 3 matrix. So it's a good thing we already did this year, because I know you all remember it from a few chapters ago. Hopefully you, even if you did not remember it right away, hopefully it's come back at this point in time. So keep working problems, keep asking questions, and as always, happy mathing.